Say no, she's here.
I'm here.
All right, Kat, whenever you're ready.
Welcome, lads and ladettes, to Aether Roundtable number 94, Sidereal Surveyor.
Thank you for that introduction. So there was recently an update to the Celestial Theodolite. I made a new spreadsheet, wanted to go over the data, had a couple of epiphanies, thought I would share everyone. And as I was sharing with it, some people had some questions. And so I wanted to kind of recap and go over the spreadsheet and kind of illustrate what it is we're doing trigonometrically, because maybe not everyone's super familiar with a triangle. Me, least of all, familiar with it. I'm just now dipping my toes in with the little arctans and tangents. So we'll get into that, and I'll show some examples of what I'm talking about here so we can all kind of familiarize ourselves with this, because once you understand the fundamental basics of it, it's extremely easy to to grasp the argument and what's being put forward. So hopefully this helps. Okay, so to start us off here, I built a little Prezi.
You're not showing anything.
Yeah, thank you, sir. It's not showing up on Discord. It
No,
should
he
be on.
is. We're good. I
No,
see it. What do you got?
I can't see it on Discord.
Is he streaming super quality? 1080 30? No, it's
Oh, I can drop it to 720.
Hold on a second. Excuse me. It did some weird glitchy thing there.
I
All right,
see it
well-
on Discord.
All right, as long as everyone else is good. All right. So to start us off here, we're going to go over some basic terminology. So a tangent in geometry is defined by a line intersection with a curve. So what this looks like when someone's talking about a tangent, you can think of this when they're talking about geometry. And then for, oh no, what did I lose my slide for? I certainly did. Okay, well, the tangent for how we're describing it is the ratio of a triangle when you know two sides and you can derive the other one. So that starts with the tangent function and the arctangent function, and I'm going to go over those now. So the tangent is, like I said, the ratio to the side of a triangle when you know one of the other sides and not the other. So in this example, for how we're going to derive the flat Earth prediction, and this excuse me, and this goes in tandem with the spreadsheet here. So all the distance values that we enter are all computated over here. So what we're going over to start with is what we're doing with this side of the spreadsheet and what we're doing with these values here. So to start us off, just with rise over run, we would do the rise here, 2227. That's our relative meters. We get that from the difference in altitude of the peak versus our altitude based off of wherever we're at X amount of distance away. And because we also know our distance here, we can do the arctan of this to get the output in degrees. So when we when we do the rise over run for that, we get 2.52, which converts into degrees, minutes, seconds into 2 degrees 31 arc minutes for our angular elevation to the mountain based off of how far away. And you can find that on E3 on the spreadsheet. And I relabeled the functions so you can kind of read the names for what they are when you go over them. So delta alt and over the distance here, the arctan over the delta alt distance, and the delta alt over the distance. So the delta alt here is right here. This is the relative alt between the known peak elevation and your elevation above sea level. And then we have the distance. And then from that, we get that, when we do the arctan of that, we get that value there. So that gives us our angular prediction for what the flat Earth geometry would predict if there's no curve drop here. Now, when we get into how we predict for the globe, there's a couple of different ways you can do it. I'll go over the way that it's described in the spreadsheet, and then Shane and I will go over the actual Heffron method here and how it differs. So what the modern globularist does to derive their distance and drop, what they'll do is they'll make a separate triangle based off of the deriving what the drop would be in meters over that distance. So to get that, they do the square of the radius squared plus the distance squared minus an Earth radius. And that comes out to be 201 in this example, where the distance is 500 or 50,700 meters to the target. And then what you can do from that, following the same way that you can derive an angle from a rise over run, they just make a new triangle here based off of that rise being 201 and then the run being the distance there. So same exact relationship, just changing the elevation number to that lower value, that 201 there for their drop. And then with that triangle, they get something that comes out to be 13 arc minutes. So instead of 2 degrees and 31 arc minutes, they get a little tiny baby triangle. This triangle does not represent, to a scale what it would be. This would be like a real tiny one. This purple line would be way down here if it were describing that. Okay, so with that number, you subtract that from the flat Earth value here. And when you do that, you get 217. You get 217 when you do that. Now, with that, so they're saying that that's their geometric globe angle from that 217 there. Now it says 220 here, but we'll go over why it says that in a second. But it's 217 when you calc that out. But then they'll want to add terrestrial refraction, and they'll say that it should be 219. So the angle that the globularists actually want for the physical angle to the mountain is 219. But when it comes out raw would be 217. Then you add 2 for terrestrial refraction, etc. But there's a couple of different ways you can derive it here. So I'm going to go over those now. The way that you can also do it is you could take the time of occlusion and subtract the drop in degrees from that, and it'll get you to 221 or 220. Oops, 1 second. My headset's yelling at me. It's telling me it needs charged. But anyway, that's how you get the 220. So that's pretty close to what they would expect or predict, but you can actually change it over here if you want to. I think you enter -18 and it'll change it to 219. So you can enter this value over here for terrestrial refraction. This has no like actual physical value to any sort of refraction. It's just an adjustment to make it whatever the globe would predict. If anyone disagrees and they're saying like, oh, you should change it to this or that, this is how you do that on the fly there. So if you need it to be 219, you could hit up that. And it doesn't change any, like it's still, just as the outcome was. But now what it continues to do here that's extremely significant is based off of the occlusion timings now. So let's see. So we'll go over the other method for, actually, Shane, do you want to help go over that now?
Over which part?
Okay, the relationship with 360 times the distance over 2 pi r, because I've heard you guys talk about this and like I kind of understood it, but as I was just making this spreadsheet and I looked at this stuff, the significance of it really dawned on me. So the way that, as I don't have this fully updated in my spreadsheet yet, I'm currently using the way that Jesse would do the prediction, and this is not
Right.
this is not the Heffron analysis. I'm in the middle of adding the actual Heffron analysis, so we can actually have a comparison side by side, all in the same frame, and do it all in one shot. But anyway, what I'm adding here is you just take 360 times the distance divided by 2 times pi times the radius of Earth, right? And that comes out to an angle, and we get 0.45618732717. And convert that to decimal or degrees, minutes, seconds, it comes out to 27 arc minutes. What you can do with that 27 arc minutes, right? So following what we just did there in the spreadsheet, because this is what I'm going to add to it. This is the actual Heffron method to determine what the drop is and where this, and it also predicts where the star is going to be, more importantly, the true position of the star, which I think is the real power of this, because people will say, oh, you're misrepresenting the globe if you don't do this method for the analysis. Well, if you do this, Like you get varying results, but even when you compare it to the occlusion timing, you'll see why it doesn't matter either way. But just to be like most accurate to truly represent the globe is built upon the backbone of the true positions of the stars, and then adding refraction to correct for where they would have to be to make them useful for the coordinate system. So if we can predict where the true position of the star is going to be using this method, we're in no way strawmanning the globe. And that's extremely important to understand, because what we're going to do is we're going to take this distance, the same distance here, 50,700 meters. We're going to multiply that by 360 divided by 2 times pi times the radius of Earth, and that comes out to be 0.456 here. Convert that to degrees, it comes out to 2722. 22 seconds. So we can pretty much ignore the 22 seconds, not relevant for this analysis. But when you divide that, okay, so wait, so 1 second. Got this value here. Okay, so when we subtract this 27 from our flat Earth prediction for the raw elevation angle at that distance and location, we get 204. And 204 happens to be the star's true position from the observer location, from where you're at. And then half of that, if you divide this by 2, you get 13.5. If you subtract 13.5 from this, you get 2.17. You get 2 degrees 17 arc minutes. So this whole idea, you get the exact value of what they want for the 217, and then to add their 2 degrees for terrestrial refraction to get 219. So to get the raw true geometric globe, this is exactly how you do it. And to verify that, you can go into Stellarium and verify the distances to these stars in this way. Where the true position is with respect to the observer location, not the peak, right? The peak is for how we do a separate part of the analysis, but to fully verify and predict the geometric globe, this formula here that I'm implementing is going to give the actual geometric angle for this mountain peak, because half of that, when you subtract this, gives where the globe is, where this star is supposedly based on globe drop. So these are equivalent. Does any of that not make sense? Oh, and let me go over this refractive position stuff real quick. So true position here denoted in red, marked by, this is where the true position of the star. And of course we know the true position of the star is the position that is referenced on the first point of Aries, which is the position of the stars on the vernal equinox, and then just adding 15 degrees per hour to that, irrespective of where anyone happens to see a star nowadays when they look at it. So they're looking at this calculated position to base everything off of where the star should be, and then they refract it out and all that. But so that's their reference point. And then from this observer location at 50,000 meters, and then the refracted star position here from here is 217. And so they want to say, or actually, no, I'm sorry, it's 219. So they want to say that the refracted position, the terrestrial refracted position of the mountain has lifted it up, and the occlusion time happens there, because the timing that it happens when the true position intersects at 2:30 at that same time from the mountain peak, that's when the star isn't visible. But at the same time, from this distance away at 219, they're like, oh, my star's not visible. So they want to use 219. So we'll definitely give them 219 and calculate it out. That's no problem. But they don't, but they're not sharing that geometric relationship with us at 231, where it was actually occluded at. Because when the star wasn't visible, if you're on this mountain peak, its true position is at 231, and that's the geometric relationship that we're starting with to build upon. If you turn on refraction at this location, you get 246, but the 246 number is irrelevant for these purposes. It's just, I just put it in there so you would know what it is if you were on the peak and you refracted it. So again, to recap, the correct formula to derive globe drop 360 times the distance over 2 pi times the radius will give you the drop in degrees, and then half of that and then you divide that by half and subtract it from a flat Earth angle of the same distance, and you will get the raw globe drop. All right. Does that anyone have any questions?
Does it matter that elevations are orthometric heights?
No, because all the elevations are done above sea level. So whatever
Well,
it is.
for their
go ahead.
So for their argument with trying to add curve back in, that's already there then with that orthometric height, or no?
So when we subtract these out, for their prediction for globular slant based off of this distance, this angle with the true position of the star actually comes out to be a different value. It's 219. Right. It's 219, right? But the star wasn't visible when the true position was at, let's see, 234. So it doesn't.
Yeah, it doesn't change anything. Gotcha.
It doesn't. Yeah. Yep.
Oh, my OBS crashed, so I had to fix that. But what D3 was asking was like the difference between ellipsoidal, normal, and geoid, and orthometrics, the actual one where they try to get mean sea level, and he's trying to see if it's baked into that, if the heights that we're using are actually tied to the ellipsoid model. I think that's a really good question. But no, we're using just the orthometric height, and for our purposes, I think that the actual known, WGS height will suffice, I think.
Yeah, Eric's actually been referencing the old ellipsoid for his GPS analysis, and he's getting pretty much the same values we are. I think there was like a 5 meter difference on Pikes Peak.
Yep.
Nice.
I like how you finally have a dude on a globe trying to do this so we can see the ridiculousness. Like, so it's supposed to be tilted away from him, right? So that's what's giving it the lower altitude and the refracted triangle at a smaller angle. Everyone sees how that's geometrically required and necessitated, right? Must be lower.
They should see it, but I don't think everyone sees that.
They don't see it. It goes right by them.
It's the same. It's the same, guys. It's just globe.
So what they're trying to do now is once Alan tries to, he says backwards derive, but it's really just calculate using the angle that you derive it.
For some reason, backwards derive is stuck in my head, and I'm like,
yeah, you got like 6 other people saying it too, so I'm gonna not say that. I'm gonna say calculate. We're gonna calculate the elevation and the actual distance. That's when they're like, whoa. I'm not going to use the refracted geometrically dropped angle I just calculated. No. If we're gonna get real world stuff out of this, listen, what I got to do is subtract the Earth curve and then subtract the refraction. Wouldn't that leave you with flat? No. This is my starting geometric globe. They said. That's where we're at now. They're like, okay, well, if you want to, that's not fair. That's not fair that your height will always match and ours never will. And that's the actual direct consequence of trying to use a refracted angle for a smaller triangle for your globe prediction. You have to stick with that. You can't just say, okay, now when we got to measure stuff, can we just borrow your time again? Hey, all time is my time, right? Or whatever. Like, no. Mutually exclusive, different angles. We go through the process of accommodating Earth curve drop, all type of refraction, that's accommodated in your angle. So when we go to measure elevation, say from the time of physical occlusion to get, say, the physical elevation of that peak, you must use the angle we just calculated. You can't just switch it to a different angle and start doing offset trig to make your prediction math. That's what the globe is currently doing. So that's why it's a good point to point out our elevations match the whole thing. That was the point with Blinn Mountain, is that, when the occlusion time is still off at such a disparity where you can't tell the difference, what's not off? The calculated angle of the physical peak and the calculated distance where you were physically at. So.
Yeah. So actually that's something I wanted to cover now to get into the next part of the analysis. Now that we covered how to derive geometric globe drop and how it's going to change in the spreadsheet moving forward. so that we can all see both comparisons for the Jesse method and the actual Heffron method. But doing the Jesse method here, we have this prediction here. So to kind of lay out what happens next, we can calculate using the tangent function this time. We can do the distance times the occlusion angle to get the distance, or to get the altitude in meters. So we can backwards figure out, or see, there it is again, backwards. We can we can computate what this elevation is here based off of the angle and the distance that we have. So from that, we get this value over here, which we're going to compare to the true known elevation distance between us. And we get this value here, and it comes out negative because the occlusion angle was higher than what's predicted by flat Earth. So the, it comes out negative, but it's, you'll see what we do with it here in a second. So just keep note of that. So we have a derived approximation for the physical elevation of this based off of the occlusion timing using the alignment of the true geometric, or the true position of the star. And then we can also computate the same thing with the distance, because we have the angle. We can use in the elevation, we can derive what the distance would be based off of that to approximate where we were at. Now there was an error in this where it was kind of circular because I was deriving it from the derived elevation angle. And if you do that, because this is based off of the distance, it's always going to cap out at the distance. So that was kind of circular. So that's fixed now. So what this does now is it derives the distance off of the difference in altitude over the occlusion timing. So it's comparing it to the actual known altitude now, and we get the distance at 49,588 meters now. And our base distance was 50,700 there. All right. And add a tab for distance comparison. All right. So we'll add a tab for that too. And then so going down on the globe, we do the same thing. So because they want to use the apparent position, they want to use the refracted position. We can't use our position over here. So we're going to use the the apparent position, which comes out to 219 for the geometric globe, or 220 here. I have it. Or you could do 217 if you wanted, if you did the raw value of the old way that Jesse was doing it. Or you could subtract the expected angular drop from the occlusion timing and get this. And that's what I did here. So that's why it doesn't trigger back to that. It kind of loops back through here, but it's derived off of what the globe predicts at this distance instead of what the occlusion timing was, because they want to use the globe. They want to use this 220 right here. So we'll give it to them. So when we derive that, we do the distance times the times the tangent of the geometric globular angle here. We get an elevation of 2074. And when we derive the distance based off of the globular angle and the known value there for the distance, we get 54,000. So they overshoot it. And then down here at the comparison that I started, we have the difference in mountain altitude elevation. So if we subtract these two, we get what the globe predicts as drop in meters based off of the approximation method that Jesse gave us to do the angular drop. So that's kind of funny because this is derived independently, like these values here, right? Like this is based off of the distance and the globe angle that it predicts, and this is based off of the flat Earth thing, or based off of the occlusion timing and the distance. So the fact that they're off by their approximated geometric drop over meters converted into an angle is crazy. And that pattern goes on for every single measurement. Now the spreadsheet hasn't been updated yet to to make the distance change here. So all the distances are still in the circular loop on these. So the analysis, the flat Earth is always going to be off by 0 on that. But when I make the appropriate correction there, it won't be circular anymore, and it'll be off by a little bit. But we can go through all the analysis moving forward on that, and then I'll have the Heffron method actually added too, so we can see them all side by side going through. And we went through every mount. Oops, 1 second, headset's doing the thing. All right, we went through all the peaks, did this same analysis here. And the reason that they're always going to be off, like spoiler alert, like I'll just cut to the chase. The reason that they're always going to be off is because their angle is always lower than what the true position is, because they don't want anything to do with that. So they want to use it from where the observer's at and say that we're strawmanning the globe, but we can derive our distance and we can derive the elevation of the mountain peak. And then to give an update to the IPUP Greenhorn Mountain or Green Mountain situation, when you put the IPUP data on the mountain peak with the elevation data for North Peak, there's no 2,000 meter discrepancy. There's no concave result. There's no what's it called? Tiny globe. There's no globe result. It doesn't give varying results. It literally can't give varying results because one of the triangles is smaller than the other one. If someone's telling you that it gives varying results and it's the same or whatever, then they're lying, because one of the triangles is smaller than the other. It's not mathematically possible for it to do what what's claimed. It gives the same result every time. The approximation is closer to flat Earth. And then so, like I said in the video there, though, optically, when you're watching the video for the IPUP, it gets occluded at the edge of the frame. And we know the edge of the frame is 44 arc minutes. You can do an analysis on it. You can, and based off of, several different factors and using stellarium and overlays, like I understand why it was argued that this peak, or that it wasn't North Peak and it was occluded on Green Mountain. However, when you put the elevation in for this peak, everything works out and makes sense. Obviously the distance will be off because it's a little bit, it's not going to be exact, so it'll change, but the numbers at the globe are off are fine. Like they're not going to change when I update that. So like I said, I don't know why optically it looks like that, but the timing of when it was occluded corresponds to this peak, and you could derive your elevation and distance based off of it. And this one was on North Peak, so we have a reference for what occlusion timings would look like on that peak, and they, these closely match. So is the celestial theodolite broken? Does it give varying results? No, when you properly I'd have the peak identified, you're good to go. Why it's off and doesn't look right, I have no idea. But the numbers speak for themselves. That's all I can say about that. Because there's no adjustments here. This is just the raw value. The rest is just plain trigonometry using tan and arctan.
I think at this point, this is probably the most lied about flat Earth piece of evidence I've ever encountered.
Yeah.
I wonder why. They're putting so much effort into misguiding and deceiving and just informing. Like everyone's just putting their hands. All the Globers know it's debunked, but they each have a different debunk, and most of them just point to Jesse, who did no debunking and created a different method. So why would they need all that effort if it wasn't a sufficient death blow?
Dude created an entirely different method to make the try. Because so with his method analysis, when you get to Blinn Mountain, you get an ambiguous elevation situation where the numbers appear to be closer, because what was done with this peak here. Nope, I don't want to go to Japan. I want to go to regular Canva. Blinn Mountain. So check this out. The true position of the star at the time of occlusion was 14 or 42 arc minutes. If you add refraction to that, you get 1 degree, 5 arc minutes. It adds 23. But this amount at the location's irrelevant. All we care about is this number right here, 242 arc minutes. If you go to the observer location where they want to do their analysis, the true position of the star is predicted to be at 20 arc minutes, and the refracted position is 46 arc minutes. So he went to a place where the missing amount would be equal to the celestial refraction correction to offset it. But the fact that it lines up with the true position and the occlusion timing proves the methodology, because otherwise the star would have been visible sooner. Because if you look at this occlusion timing that we used to derive everything, when it wasn't visible versus the refracted position, there's a 4 arc second discrepancy in that. So this point source of light, once it crosses 4 arc minutes, once this crosses 4 arc minutes of distance to the with respect to the peak, it got physically occluded. It's not at 20 arc minutes, and it started appearing sooner. It's within that same degree of tolerance that Goose showed when he has his rig with no refractive medium, and you line up the stick with the dowel, and the light source is right next to the stick. And then when he adds the refractive medium and then moves the light source to when it's no longer visible to the observer, and then he removes the medium and puts the stick back, the light source is further back because like the physical occlusion is changed, because it's when it actually is intersected, but the angle changed because of the refractive medium. But to the tune in which they invoke refraction and as if it replaces it 1-to-1 is absurd, and this shows that completely. There's only a 4 arc second difference between their apparent position and the true position intersecting it at that elevation.
4 arc minute.
Oh yeah, sorry, 4 arc minute, yes. Does that make sense?
No, big fatty weirdo.
Oh, it's Jack. So I'm sorry, guys. I'm new to this. I'm catching up. You're measuring occlusion elevations at specific times, right?
Yes, sir.
No, we're not measuring the elevation. We're observing the
No,
occlusion, and we're using that time to get the angle, right? We're not measuring the angle there, are we?
No. The occlusion time is an elevation, right? It corresponds, like this time has a alt as to it. So he's saying you're measuring the time of occlusion, and that gives you an angle. That's what you were saying, right, Dan?
Well,
Yeah, you're just capturing when at a specific elevation when these stars are occluded and at a certain. So you're solving for a triangle, basically, right?
Yes, 100%. That's exactly what we're doing.
This is a fucking body bag. This is crazy. And how many people have been contributing to this? This is sick.
Dude, so this is awesome. So Mike did a ton of peaks. So Pikes Peak, Blodgett, Mount Rosa, Blue Mountain, Green Mountain, North Peak, Cheyenne are all Mike's, and he's got a ton of stars with him as well. And then Jesse contributed a few at the same peak, different distances, and Kat and I did two peaks, 2 different distances, and Goose did one from Mount, what is this? This one right here, Varley SE2. He did this one from the.
It's amazing because it's simple. It cuts off so much of the fat. It's so simple in a way.
Dude, it's almost too simple, right? Because they're gonna invoke refraction, and it's like, okay, but still, we can derive not only just going off of the angle that it was occluded at, we can derive what the elevation would have had to have been, and we could derive what the distance would have had to have been, and we smoke them every time because they want to use the refracted position from where they're at, because they're locked into that post-diction lifestyle that is known as the globe.
Yeah, and I've been tuning in. I'm catching up on this subject because I've been out of the community for a little bit, but I tuned in last time you had Jesse and Ruhiff, and it's just, this is amazing. Anyway, just wanted to tune in, just clarify for my own personal notification, and just say, like, you guys are goats, man. This is insane. So keep up the good work.
Thank you, my good sir. We just work here, as we like to say. But shout out to Mike. He came up with this in February, figured all this out hella early on, and I'm just now kind of catching up to this part of it and the significance of that. Especially, were you here for this part of it? The how to derive the globe drop and how it equals where the star's true position is, dude. That's preposterous, dude.
Dick. It's retarded.
How the whole thing works. It's how the whole guys has been pulled over. That's what Mike said. That's what brought him over to our side when he made all these realizations, dude.
That's
Yeah,
so
shout out to
crazy.
Mike. That's all I got. Please don't let me interrupt again. Cheers.
No, you're good. So yeah, we don't have
Dude,
to
we
go
should-
through all the peaks, but I covered all the big points of contention and the analysis. When you do the actual method and you do the analysis, it's not even close. When you do a custom thing and get a different drop angle and ignore this part of the analysis, then, like, you know, you can kind of pretend that it gives globe results, but no, when you actually get your Pythagoras theorem on, it's over.
Maybe we should field questions from our FE friends so that they can answer, you know, because the Globers make the same objections, right? So maybe they've heard some objections and they'd like the quick answer to it.
Why can't we just use a different time?
That's my favorite. Listen, I live on a globe, so all timings are globe timings. So all the timings are for the globe.
What's another
much the argument.
objection? Dude, I haven't even had a good objection that isn't a complete strawman of our position. Like, I don't even know what to say on the spot.
Yeah, 13 weeks. Jesse made a simulator and 14 hours of nonsense with Jesse. Not one actual refutation put forth. A simulation of a totally different method to try and strawman and obscure and kick him up. Sure. One or two of those. But a direct rebuttal, 0 and counting.
I guess the purpose was just to make it look like it was ambiguous and gave different results. But
Well,
as
that's
you
what he
can-
told Ruhu if the purpose was anyway. Who are we to second guess that?
Yeah. But as you can see, when you do the full trig on it, you can derive results that the globe does not agree with. So I'll just keep it on Pike's Peak because it has the correct distance one for now.
Yeah, my funny take on this is you can't have your refracted triangle cake and eat it too. Right? You can have your refracted triangle and pretend that it matters and have it not match occlusion times. But as soon as you measure real world stuff to it, they have to go back to the actual true flat earth angle and they try to obfuscate and duck and dodge to get back to it. It's so funny.
How do they even try to get back to it if they already subbed it out?
Well,
what does it mean that I didn't do, like, the only angle that they have is an apparent angle of the star at 219. So what are they even doing to try and say that it's also 230?
Well,
Because that would require them to acknowledge our position, which would invalidate their position.
so you know how they calculated geometric earth drop and refraction to get that initial angle
For their drop prediction? Okay.
to get 220/219/217, depending on who you ask.
Yeah.
Well, what they do is, as soon as you got to use that to measure real world stuff, you got to subtract geometric earth curve or add geometric earth curve back in and then subtract refraction back out so that you can get back to the actual true angle that you started with. And then they want to take measurements from there. It's the most ridiculous thing I've ever heard, because inherently when you're at that point, they realize, oh, wait, this won't come out right. And so they go, that's not fair. In order for it to come out right, we have to undo everything we just did. So that's what they do.
Wait. So that means that
They use the flat. Yeah, they just pretend not to. It's like when you add that stuff back in, it goes back to 232. So that's what they try and use. It's the most ridiculous thing.
What do you mean?
That's Coffee's contention. He's saying you got to add it back in and then subtract the drop.
My God, that's so retarded. Can
this be used to? Can another of his contentions was that we can't use this to predict anything. Is there any way that this can be used to predict things prior to actually making the observations?
Yeah, I can predict my location.
Yeah, you know what? Somebody else brought that up to him too, and he was like dismissing it.
Well, I mean, like dude, if you have an actual point and like they dismiss it, it's like, where do you go from there? Like, do you come up
Yeah,
with another
right.
point for him to dismiss? Like, I'd rather just like,
right.
Not sure that he understands the premise nor the point subsequently. So
Yeah, of being able to, because Stellarium doesn't know where you're at, but you can get where you're at based on the timing.
yeah, to get the distance, you just take that angle, and then you got your triangle because you already calculated the elevation based on the tangent, and it all works together, man. It's beautiful. But the whole point is that they have a different size triangle, right? It's lower and smaller, so that when we're calculating distances, they'll always be different. That's our goal, intended mutual exclusivity, meaning it would lock you into one result or the other. Because they like to do this thing where they change all their data until they get the right result, which is what they're doing right now. They're in that process, right? Trying to use the flat and add it back in, subtract it, whatever they try to do before they subsequently. I mean, one of the objections the last time was, if this were true, why are all the Globers still aggressively objecting? It's like, well, if you present something that undoes everything, no one's going to acquiesce and lay down and be like, oh, you know what? This proves it. Even if it does, even if it's solid, I don't think anyone's ever going to just do that. So I think people are expecting, listen, if this was the breakthrough you guys are saying it is, I would see on the news or whatever.
Yeah, this is one where you can't rely on like audience reaction to understand it. If you want to like argue it, internalize it, and like really understand it, the best way I would recommend is grab one of the spreadsheets and just make your own spreadsheet. That's what I ended up doing. And it made it way easier to understand and interpret it. And I had like several epiphanies going through it that I should have had a hell of a long time ago to better understand this and move it forward. So
that's what I told him. That I said, why don't you get the spreadsheet is out there, get the spreadsheet, do your way, and then come back and everybody can discuss it and why it should or shouldn't be,
Yeah, work out one of the examples yourself. Like, go look up an elevation. Like, understand the process, and then try to plug in your own stuff to do it see if you match what's on the spreadsheets, right?
Right.
And then if you do that with both spreadsheets, you'll notice that the methods are entirely different.
Yeah, dude, that was a big one for me today when you showed me when we went through that. Do you want to pull up your slide and go over it real quick so we can kind of have like a nice breakdown of what you've been laying out too?
I think you nailed it, dude. You've been absorbing it. You asked me to do it, and then you immediately summarized it nicely and perfectly. So I think it was fine. It's always good to see, right? No need to hop in if you're nailing it.
Yeah, it just like I totally forgot about the true position. I kept thinking in terms of the refracted position because they want to go here and talk about this. And I forgot when we were talking about how the 2 pi versus the 1 pi, like having it comes out to be exactly half for what the mountain was. I was like, but it was just kind of lost on me. And earlier, right when you left, and I had just got this working, I had an epiphany, and I was like, oh my god, I became the scene in that Vegas movie where he's all the math symbols are floating around.
The Hangover.
yeah. It became the scene from The Hangover.
Because Jesse was like pretending to do the Heffron method by completely following different steps.
Right. That dude.
And then he was like, look, it doesn't work. And I'm like, well, Jesse's path of horse shit doesn't work. I don't know where the Heffron method went, but that still works fine.
Yeah, now that I see the difference, like mechanically, that's not gonna fly anymore. That's over with, dude. Doing a completely different analysis, dog. GTFO.
Dude,
anyway,
did a whole holiday tour with that different analysis, going on McToon's side, telling him how he made his own graphs of all different data, then telling us that we fudged everything, and then presented his not Heffron method as the Heffron method maliciously. Like that's the kind of person we're dealing with.
Well, it's fine. Now that I understand it better, that's not going to happen.
I see. My OBS crashed twice. What is going wrong with this?
Sounds like Windows sucks.
All right.
Arch Linux strikes again, boys.
Said can't connect the stream key issue. It's like what? Whatever.
You guys know that channel? It's like I think it's called like Two Eyes Brown, One Blue, or something like that, where he does these excellent animations.
Yes.
Bro, that I think this needs like an animation breakdown like that for like the world to see. We should pay that dude.
Yeah. Pay him to end his career or whatever. Like, hey, will you make us a banger model simulation thing and retire?
You imagine if D3 came to the group and he's like, guys, I have this hypothesis. I think it works. It's really cool. I'm going to bounce it off you guys. We all listened to him, outlay it. We all went, like, cool. All right, I'm going to go home and I'm going to test it. And then I came back and I said, oh, I did something totally different. But by doing so, I know that your hypothesis is dog shit. You'd be like, could you not wait? So you didn't test mine? Well, no. I mean, I made mine, but mine shows that yours is wrong. What? Did you test mine? No, yeah. But well, I mean, I did this thing that's called yours. Like, what?
That's preposterous.
In what community is that allowed? Like, what the fuck?
Yeah, and you know what I like about this is you could verify the correctness of it with the true position of the stars in Stellarium for any of these.
Yeah, as Mike put out when he first came up with it, not only is it removing their biggest wild card, but it's using their own tools against them. And he took some delight in that, if I remember.
There was a little grin. He was very, very happy to see that happen. But yeah, if anyone, are there any more questions?
I keep getting this question all the time. If you move the observer to the peak of the mountain, wouldn't that change the elevation angle to the star?
Yeah, but that's true on both models.
Right.
But we're at the mountain. We don't move from the mountain. We're always at the mountain.
We're only referencing the true position and the angle that it wasn't visible. And it just happens to be the same angle that, or close to the same angle that we calculated.
But only ever from the mountain. So.
Right.
Like there's no moving it to the mountain.
Location, then it's like 204 for the true position, but then you wouldn't be able to see it because, if you
it would be hella refractor. They say that it's refracted up to 217 or whatever, but
as crazy already.
Yeah, but as we found out earlier, within 4 arc seconds of the intersection, the star is no longer visible for an observer X distance away. So that's
minutes, right? 4 arc minutes.
Yeah, I keep saying seconds. Sorry, arc minutes. Yes.
It's all good. Gotcha. Yeah, that's pretty much the only one I keep getting.
Yeah, because they keep doing that because as soon as you realize what we're putting forward and you realize, well, at the mountain, I lose every time. What can I do to change that? I know that I'm right because Earth is definitely a globe and these guys are wrong. So what about, what if I, and then they go down this road of endless hypotheticals.
If I do an entirely different method, change positions, do a transformation, reference geocentric coordinate systems, involve the solar system.
Still wrong.
What would they say? I mean, let me see if I could ask this right. I mean, if results could be derived without inputting coordinates into Stellarium, wouldn't that mean the model is independently valid?
You're coming in super low, Mr. Xavier. Just going to say it. I couldn't hear you.
Is that me or is that? Hold on, let me change the mic.
No, it's yellow.
Yeah, so, I can hear everybody else except Professor X.
So, Zave, if you use it the way that it's designed, it's internally consistent, and you can't find out if it's valid in that way. The way that we're using it, they're not able to derive the correct location. So, what it's showing is like the curvature that they say exists, doesn't exist terrestrially.
Right.
I like the point that you make all the time, Alan, is that previous to this, our contention was that this is an optical drop off, and you guys were always claiming it's physical. And this is by far the best method that's ever been put forth to differentiate between those two. Okay, well, is it actually a geometric physical Earth curve drop off, or is it an optic compression to facet of perspective? And lo and behold, it doesn't match the physical geometric Earth drop off ever, not once. So, not physical, I think, is the conclusion.
Would they agree that only the flat Earth model aligns with physical occultation timings?
That's all it does. I mean,
first they said it was cherry picking, and then it was just this one peak, and now it's none of them because the simulator simulates concave. So,
gotcha.
But also, Zave, did you notice that the difference in how much they're off in the elevations based off of occlusion timings turns out to be what the geometric drop over distance is in meters?
Oh yeah, I caught that. Yeah,
that's preposterous, dude.
Wonder how they created the model. Oh, just like that. You're looking at the bare bones of the system, dude.
Yeah, they were like, how far would it have to be?
If the globe was a matrix, Alan is reading code right now. Get the
Yeah. Oh, look, there's our concave. Oh, wait, that's not concave at all. It's just regular flat Earth versus globe results in the flat Earth one.
The only way, literally, we discovered the only way it could go concave is if you simulate everything and fake it and then push it to the extreme past where any observation would go. So that's how you know he's not doing real observations and has no real data and is doing something totally different because he mentions concave, which means someone pressed his slider too hard. That's it. That's all that means.
Someone's quadratic refraction formula coefficients acting up again.
Yeah, like that's not real. That's Jesse's path of horse shit or whatever.
All right, well, no need to say all that, but we can, if there's no further questions, see Dr. Mike's here. Dr. Mike, do you want to add anything, my good sir?
Sure, I'd be happy to say a few things. Just a minute or so ago, you made a profound observation.
Is anybody else hearing him? I can't hear him.
Yeah,
oh,
we hear him.
Nope, we can hear you.
Okay.
I can hear him.
Okay, I'll keep going then. The profound observation that I think you made is one I think we should confront them with a lot. Is basically the only thing we need to know is the peak, what star it was, and what time the peak occluded it. And we don't need anything else to look up the elevation of the star in stellarium. And what's profound about that is it doesn't know where we are, and yet it comes up with the flat Earth angle to our location wherever the heck we are.
Right. Right.
And I think we need to keep emphasizing it until it finally dawns on them. Not only is this not cherry picking, stellarium has no clue where we are.
Yeah.
And
right.
And this is so simple. Literally anybody can do it.
And that's when they say it's only a coincidence.
Oh, it's rubbish, mate, or is that rubbish?
My position is it's rubbish, mate. Like, all right, dude, I can derive my position. You can't.
I disagree.
It's rubbish.
Okay.
All right. So like that is the power of this, and we'll, so understanding this is key.
So I noticed a lot of our globe Earth friends are having a problem with the globe Earth peak to observer distance, and technically that's not being calculated the right way, and I'm not suggesting you change it, but instead of dividing by the tangent of B7, if you divide by the tangent of E13, then it will come up with the correct distance, the same distance that we get for flat Earth. So eventually they're going to figure that out and they're going to confront you with that. So just be prepared for that when it happens.
What now?
They're going to use
Hey,
the lower distance.
Dr. Mike, do you know anything about
Hang on a second.
spherical harmonic coefficients?
Hang on a second. Change what now on distance? Because my distance
it's
now
in E17.
Damn it,
Not
I
an
can't hear him again.
E17.
Can you hear me, Alan?
Yeah, E17. Okay, E17.
One more down.
Okay.
Oops. Yeah, E17. So where it says geometric globular angle, that's weird. Because on mine that was showing the E7.
It is. Yeah, it's E13 now.
Okay,
It's
so
the
with
delta alt minus the globe occlusion angle, or globular occluded mountain angle.
you're
yeah.
Okay. I think that's a different formula than what I was seeing.
Yeah, I just updated it earlier, I think.
Okay. Well, what I found is if you divide the globe mountain altitude by the tan of the geometric globular angle, then they have the same distance as we do. So eventually one of them is going to discover that and they're going to challenge you on that. So just be prepared for that when it happens.
Oh, that's because the globe angle is derived from that's because it's derived from the same distance or whatever. So that's what was happening for the flat Earth one. That's why I changed it, so it's no longer circular like that.
So I know why it's happening, but our globe Earth friends don't seem very bright, and they haven't figured this out yet. But eventually they will, and they'll say, "Well, you need to do it different." And if you do it different, you come up with the same distance as we do.
Changed it to I changed it to the delta alt over the tangent of the occlusion angle now.
Wait.
To get the
I like the
distance.
changes you made. Is this version somewhere where I can grab it?
Yeah, it's the same. It's on this. It's the same link. I'll send it to you. I just updated this. I'm going earlier.
I know where the link is, so you don't need to send it to me again. But okay, you'd send it anyway, so that's okay. Yep.
So couldn't you do the same thing with the elevation we're deriving then and use a different angle?
So if you use the elevation to do the distance, then you'll get the correct distance every time, no matter what, even if you make this an absurd angle. So that can't be right.
Yep, there's a lot of things you could do different, and I like the way everything is done here. And it points out that and if you ever change terrestrial refraction in B14, what I'm about to say will become untrue. But while that's 0, you can take the flat Earth delta altitude in E5, add it to the globe Earth drop in E11, and that will be always the globe mountain altitude difference in E15. Oh, E16, sorry. But and you already knew that. You just add one to the other, and that explains their difference. So it's always the globe drop, like you already knew.
Yeah, that's one of my favorite things. I couldn't believe that it comes out to be the exact same. It's hilarious.
And then I'm glad you picked up on the fact that 360 times d over 2 pi r is the alleged globe tilt, and it gives you the uncorrected angle from the observer location, because the globe Earth guys still don't understand that. And I'm surprised. well, Ruhif probably knows it because he sent surveyors to my house and they came up with that angle. But even
Wait,
Ruhif,
I
did
don't
he
think he
send
actually did.
did he send surveyors? Were there? Did you
well,
see
he
people
denies it
there?
now. He was bragging about it, and he put a picture of the dog sign in my front yard.
Oh,
But he
that's.
denies it now, and I think the legal ramifications of what he did is finally dawned on him. But
I think the Google thing that's from
I
Google
think he
Earth. I
just found a
think.
Google image of where I think he just looked it up online. I don't think he actually did send surveyors. He threatened it, but never did it.
ah, oh
Yeah.
yeah, okay. I didn't. It didn't occur to me. He might have used Google Street View or something.
Yes.
Yeah.
Yep.
So that makes sense.
Yep.
Yeah, that would be crazy if he sent surveyors, had him take a picture of your house, like, yeah, dog, we got you. That would be nuts. But no, you could
But
see the thing
anyway,
from Google Street View.
whether he
Is that
did
what
or
he
he
means by
didn't,
tap the sign?
Dude, oh no.
maybe.
That makes more sense than anything else. Damn.
Yikes.
I asked Google what that meant, and it said it meant something like push the button, which didn't make any more sense than what he said.
Right. Our Australian correspondent has confirmed that it's like an expression of like, what was it again, Rick? Are you there?
It's a term of endearment for Australians.
Tap the sign.
They say, "Oi, mate, I'm gonna touch your sign."
That's a term of endearment, huh?
Yeah, they're like, "Oi, mate, I'm gonna touch your sign."
All right, I need to ask Rick what the hell it is now. But that's okay.
No, it's what I said.
Well,
You know, I'm gonna touch your sign, bro.
Whether he confirms or denies it, he was claiming that the professionals measured 2.04, which you figured out that's 360 times distance over 2 pi r. Subtract that from the flat Earth angle, and now you have the flat Earth angle from the observer, from the alleged the alleged globe Earth angle from the observer location. I'm getting my old
Yeah.
terminology all messed up.
Yeah, that's
What I like
preposterous.
What I like about yours is that the actual, when you're doing the opponent's prediction, you can confirm it using Stellarium. It lines up with certain ways to predict it. And when they try to, predict their own, they're all over the place. Ruhif predicts something different than Jesse, which doesn't match Stellarium, which is different than what we get. So someone's doing a consistent, reproducible method, and someone's doing horseshit.
Yep, and I truly believe we have to rub it in their face that the way we're doing that gives us the consistent right elevation. Stellarium has no idea where we are. Corrections off. So all we're doing is telling it what the star was and what time we saw it and on what peak. And it tells us what the flat Earth angle is. How did it know? I don't understand. That's rubbish, mate.
Dude, why does Stellarium have a flat Earth built into it or whatever? Why is it giving us flat Earth lies?
So, Dr. Mike, I have a question. You said before you are familiar with the coefficients that I mentioned.
Oh, could you repeat your question? Because I kind of lost track of it during the other chatter
Okay.
that was going on.
Okay, so when I was researching the geoid, I came across one of the things that they're using to tie it to give it its kind of shape and heights, and they're using spherical harmonic coefficients. I don't know much about those. I was just wondering if you know about them a little.
So I'm not really familiar with those either, and
Okay.
but I think all of that is part of their continuing push. But the tactic I noticed they've been using on us is they want to argue our data is too sloppy, it's not accurate enough, and they push us to more and more and more accuracy until we get it perfect, and they say, "Oh, that's too good. That's no good. You're cooking the data." So they're just trying to run us around in circles, having us chase our own tails.
Well, not these guys. So what I'm referencing is NOAA, the agency that handles all of the data for this stuff, for building the geoid model and connecting it to the ellipsoid model. So what I'm thinking is, like, if somebody in here knows how to handle that, what I'm thinking is Stellarium has all of this data that's very accurate, connecting the sky to the ground. Points are all accurate. It works. We know that. Underneath it all, it's being tied to the geoid and the ellipsoid model. But if we can unravel that and kind of reverse it, we can, I think, begin to build our own model.
Using geoid gravitational directional vectors, bro?
The geoid, so the geoid, it just measures the intensity of the gravity, the downward vector.
Right. So the intensity of the variance of 9.8 as a metric all over
Right,
the Earth.
right, which is only ever downward. But then it gets, what they're doing, they use something called those coefficients that I mentioned and other things to connect it to the ellipsoid model, and then that's how, then once they have that connection, then they can do the orthometric heights, right? And so if we can reverse those things that they're doing, and get back to like the original data, which would be plane survey and just the gravimetric data by itself without it taking shape, and then we can create our own model. Instead of using an ellipsoid model, we can use a different model. I don't know how to do it, but I'm thinking that can be done that way.
I don't think that'll help us. And like I said, they're trying to push us to greater and greater accuracy so they can then turn around and claim our data is too accurate and it's got to be cooked. And star occlusions will never be all that accurate. It's hard to even get it accurately to plus or minus 1 second. I think it could be done with the right equipment. It could be done, but even that's only going to put us within 15 arc minutes, and 15 arc minutes is probably something like plus or minus 10 meters. And so we do all that work, and then we're still stuck with the same plus or minus 10 meters we had before we did all that work. So I actually totally revised my spreadsheet to use NOAA calculations, because originally I was using movable types, and this slide that's up on the screen, that uses the movable types data. And for all practical purposes, it gives you the same result either way, even though the NOAA data is like 10,000 times more accurate.
Yeah. Oh, by the way, guys, they're going to be phasing out a lot of the way that plane surveyors do their job. They're going to be changing it to where, like, if they want to submit their data anyway. In order to, coming soon, if they want to submit their data, they're going to have to derive it from I think it's the NGIS system, which is automatically the geodetic prior to them even dropping the plumb line and all that. So that's a interesting move.
Nice. They're pre-cooking the globe to make it like idiot proof.
Yeah.
So like
Yeah.
just the word theodolite will be synonymous with ball curve.
Yeah, so instead of when you look up in the sky, it's globe. Now when you look out on the ground, also globe. Sorry.
Yep.
It's a globe measurement.
That's
So I think I just.
I have a quick comment, if that's okay. Hello?
Yes, go ahead, Lily.
Of course.
Oh, sorry. Dr. Heffron, I just wanted to say that your method and your experiment is so brilliant in its simplicity. And I say that because when it's so direct and simple, it's almost impossible to screw it up. So it's sort of foolproof. And I think that that's because of the brilliance of the simplicity of it. So thank you so much. This is what did that guy say? This is a body bag or something? It's phenomenal.
Body bag. Yeah, Doc, the fact that I can understand it, and I am retarded, so.
I feel the same way whenever I understand something. I'm like if I get it, But yeah, I'm super excited about this because that was kind of lost on me. And then like after going through it and seeing it myself and then like making that connection, I was like, oh, what they're doing is not this at all. So shout out to the boys who were keeping me on the tracks there.
Well, and I don't want to take too much credit for my own method. I like pay attention to the thoughts that pop into my head from wherever they may pop from. And I think God leads us in ways that we don't realize we're being led. And so if we listen to ideas, we investigate them, we explore them, we think about them, I think God will allow us to have credit, but I'm not sure I deserve the credit for my own method.
Well,
No,
okay.
no,
So
totally.
God worked through you then.
We'll just call it the Liliana method and give her all the credit. Everyone on board?
Oh, that's fine with me.
Bru-
No,
Brush
well,
brush tail braid.
how
Must have been coffee.
I thank God that he came through with that idea through you, okay? We'll leave it at that.
Yeah, so doing the Liliana method, it's really foolproof, and
I can't
there's
believe
no-
it took me 6 months to grasp the intricacies of what Liliana put forth all those months ago, to be honest.
I don't know, boys. I think we're going to have to take it one level up from foolproof, because what the Globies are making clear here is that what we present has to be Globie proof. And I think that's a whole new level.
It's a whole new level of proof, huh? Yeah.
You have to be able to withstand the intellect of the Globie, not just the fool. And then we would really have something, I think.
Like, how do you protect it against malicious representation or misrepresentation or whatever? It's a whole new barrier.
You're on the path. You're on the path now. Yes.
Yeah, that's crazy.
But yeah, so the most lied about flat Earth evidence ever. Here you go.
Dude, that's awesome. All right. Well, if there are no further questions, we will go ahead and wrap up. We'll see you guys on Thursday for Clubhouse. We're going to be doing an update to this as well, sharing the information, and hopefully by then we'll definitely have the spreadsheet more refined and corrected there with some additional comparisons to go over, so we can compare the Jesse method and the actual quote unquote Heffron method, which by the way is just triangles. It's nothing too crazy. But we'll go over that. And then on Sunday, we'll go over it again on Glowbusters.
Came right home. I love it.
And then the next week will be something new, I promise.